Thank you for coming. I know this conference is about energy, and this is the first time they are actually doing something with water, because there's a huge energy-water nexus at the moment, and especially in these regions, like in Middle East, in North Africa, South Africa, even other Asian countries. Nowadays, water has a big impact on energy consumption. So, because I've been working with salinity gradient processes for the last 10 years, I wanted to give some information about what I think and what it should be done. What happened in the last 10 years? Why did I choose this one? Salinity gradient process, FO and RO, are they really the answers we are looking for desalination and sustainable energy production? The reason I chose this one, in the last 10 years, we had a lot of different publications, a lot of projects, a lot of high-level news saying that we can make desalination free, 100 times cheap, or we can produce as much as energy we want just mixing two different types of water. But what happens within 10 years, for example, with the FO, we actually didn't come very far. We had some niche applications, but we kind of stuck at the point. So I give this one to my MSc and PhD students as part of my module in the UK to tell them where to start if you're looking for a new application. Okay? So it could be a little bit heavy on the thermodynamics or theory. I will try to make it more easy to go through, but I think it's very important that we understand what we can do and what we cannot do, and what we should tell the people when somebody comes and say, I will reduce the desalination cost 50%, we should actually think about it and ask them how you're going to do it and what are the bases of that one. So we all know desalination is the fastest growing market in the water treatment, and this actually was the prediction for 2018. We almost doubled that prediction in the market share. So desalination is going to go further, and because of the energy consumed by the desalination, either thermal or membrane, we will have to consider it as a major energy outcome from wherever we are working. So first, the thermodynamic limits. When somebody says about energy, when you mix salt and water, there's a certain energy release. It's called Gibbs function here. It's the basis of second thermodynamic law. If you mix salt and water, the release of this energy has to be given back to the system in order to separate them. This is the law. This is the thermodynamic law. You cannot break this law. Okay? So we have to understand at first, if you want to separate water from the salt, you have to give this energy. This is the mixing energy, and we call it in desalination Gibbs free energy of mixing. Okay? So if you look at it, the thermodynamic limits, we can convert this one into pi here, which pi is the osmotic pressure. So this mixing energy directly related to osmotic pressure, and by using this osmotic pressure, we can calculate how much hydraulic pressure we need to reverse this pressure. Okay, if we have enough hydraulic pressure on the opposite direction of the osmotic pressure, then we can start creating water. The reason we are doing this at this point, it depends on, in desalination, how much water you want to draw. So if it's a 40% recovery, you need different hydraulic pressure, 60% recovery, you need different. The reason is this process is dynamic. At the beginning of the desalination, here, you might need only 15 bar of pressure. And that is for the zero recovery point. But if you want to remove 50% of this seawater as drinking water, you have to apply the osmotic pressure at that concentration. So this is very important. When somebody tells you about recovery, the most important thing is what percentage and what pressure you want to use. Of course, we have around 20% additional we put on this pressure to compensate the losses within the system. Therefore, we have a process here running at this pressure, and you have this irreversible losses from the process itself that you cannot recover. So this is based on the thermodynamic limit. If somebody says the thermodynamic limit, in an ideal desalination process, which means there are no losses, your hydraulic pressure has to be calculated based on the osmotic pressure at the percentage recovery. You go to Middle East when you have a seawater of 56,000 TDS, at that point 50% recovery doesn't make a lot of sense. 50% recovery will put your brine at 120,000 ppm. At 120,000 ppm, you need around 100 bars hydraulic pressure. So we have to be very careful which water we are talking about, which recovery we are talking about, and what are the conditions. There are a lot of misinformation in the water sector. A lot of people come and say and claim, we do this, we are the best, we can do 60% recovery in this water. We have to approach it in a much more careful manner. So if you look at the minimum theoretical energy consumption, if your TDS is 35,000, this is around Mediterranean Sea level, the 0% recovery when you get the first fresh water out of the membrane, first drop, you have to put at least 0.7 kilowatt hour per cubic meter energy to get the first drop out. If I want 50% recovery from the Mediterranean-based salinity water, you have to put at least 1 kilowatt hour per cubic meter. So this is the thermodynamic limit for this TDS and for 50% recovery. So it will be different if you go to Middle East, it will be different if you go to, Black Sea between Turkey and Russia, it will be very different in Singapore. The other thing is theoretical and actual energy consumptions are also different. So the theoretical minimum we said 1 kilowatt hour. You have 20% practical losses from the pumps, from everything. Let's say 1.2. Actual minimum for SWRO, because we have a lot of losses along the way, a lot of pumps and recycles and whatnot. The actual minimum for SWRO is 2 kilowatt hour per cubic meter. However, this does not include any pretreatment, any intake, any post-treatment. If we include all of those, the number you get is between 3 and 5. Depends on a lot of different things. You can have a really good water, like in Chile. You don't need a lot of pretreatment. You can just pump it directly through the system. Or you can have a high pollution intake, like silt and whatnot in the Middle East. Then you have to use a lot of pretreatment. You have to use like DMS, DMF, and even UF. So if you look at it, where we can save the money, where we can save the energy, is based on osmotic pressure here, reverse osmosis process, which is only just below 70%, and 41% power for the entire system. So the actual energy savings here is already capped at 48%. If it's zero energy process, the maximum you can save is 40%. So you have to be very careful. And this is what we come from. Before this device, this is called an isobaric pressure exchanger. It recovers the pressure from brine and gives it back to the inlet. Before that, we were working around 7 kilowatt hour per cubic meter. What happened after this device, we went down to 3.5 depending on the intake. Now what we are looking at is right about 2 kilowatt hour per cubic meter because your thermodynamic minimum is right here. So we are hoping within 5 years. This is a typical desalination plant. This was done for high TDS seawater in Qatar. We did this one for 42,000 ppm. You have intake and pretreatment. You have a fixed power consumption. First stage SWRO and second stage BWRO. Why we have two stages? Because membrane desalination does not give you enough water quality in first pass. Almost every case, we have two stages. We have to bring the TDS around 25 to 50 ppm so we can reconstitute it with calcium carbonate. Otherwise, it will be very dangerous to the distribution line. So we have two stages of reverse osmosis and outfall structure. This is around 3.8 kilowatt hour per cubic meter. The only possible energy saving here is from the first stage SWRO. Why? Because all the other processes are already being optimized years and years in advance. If we look at it, if we calculate what is the minimum theoretical and applicable minimum, applicable maximum specific energy consumption reduction for the whole process, for the SWRO process, is 23%. We can reduce only this part as 23% if we apply new technologies. If we expand this one to the entire process, our savings should be capped around 16, maximum 18%. So this is the limit we are working with. No matter what technology you come up with, no matter what you do, this is the energy or this is the savings you can add to the process. So this is very important to start with. The reason I'm going here, because the first thing I want to talk is the forward osmosis. When forward osmosis came out, they say this is a natural process. You don't need any power, you don't need any pressure. The water just flows by itself. But again, that flowing water by itself, on the other side, the draw solution, you have a very high osmotic pressure, which means that osmotic pressure already has a Gibbs free energy of mixing already released. Then you have to separate that one, the draw solution. So that was a big problem. And we learned a lot of stuff. We can say 50%, 60%. I will produce water for free. We heard a lot of things for 10 years. A lot of people get a lot of projects. They'll get very famous. But now, when we look back, we can see the difference, what really happened and what was promised to be happening. First, the thermodynamics. I will just go simply. This is, let's say we have an osmotic agent here, and we have a feed water, and we separate them with a membrane. It's a selective membrane. If we do nothing here, the feed water with no salt will flow through the membrane and increase the volume on the osmotic agent. This is forward osmosis. This is a natural process. We can add additional pressure to the feed water and increase the flow rate from feed water to salt water. This is called pressure enhanced osmosis. We can apply just enough pressure to the osmotic agent, not enough to stop the flow, but enough to just keep the pressure constant and sustain a suitable flow from one side to other side. So again, in pressure retarded osmosis, we are not converting the direction of the flow. If you apply enough pressure on the osmotic agent, then this is reverse osmosis and you can produce fresh water. So this is basically the mixing of salt water and clean water. So we have oceans, we have rivers, we have a lot of different salty and non-salty water sources. So it is predicted that we have 1,700 terawatt hour global potential coming from this. But there is also an exergy idea how much of this power can actually be converted to a workable energy. Okay? If we are talking about 5 ppm salt water with 0 ppm salt water, mixing this one will not give you any energy because it's so small that power that you are trying to recover is going to be lost on the system because your system has inefficiencies. Nothing is perfect. So for the thermodynamics, this is the flux. What I want to say here, I'm not going to go into too much detail. All the research we do about forward osmosis, we use reverse osmosis experiments to find the constants. For example, A here is the permeability constant for the membrane. We find that one by using reverse osmosis experiment, which doesn't make sense because as we saw, the flow patterns are completely different. We don't have positive pressure in forward osmosis. On the other hand, reverse osmosis is based on hydraulic pressure. We also use this experiment to find the salt permeability coefficient the opposite way. And we also calculate our S parameter, which tells us the thickness of the membrane we need. It's very important for membrane development. We found all of these by only using the reverse osmosis experiment. So there's a big mistake that we are doing, and when we have experimental results coming from this approach, that S parameter is very different than what companies actually find, like Toyobo, Toray, when they actually apply this on the process. It's very similar to the pressure retarded osmosis. The only difference here, now we have a hydraulic pressure on the same size with the reverse osmosis, but again the flux and the salt reverse flux are different directions. What we do here, we again often use a lot of reverse osmosis experiment to find out these constants and important parameters, and then we calculate our process and how efficient our process and how efficient our membrane that we apply in this process. We start with the forward osmosis. There are a lot of mistakes that we are doing. First of all, the first part here is the forward osmosis itself. What we have a draw solution, high concentrated draw solution, and we have low concentrated feed solution. If we give these to an FO system, forward osmosis system, water will flow through the membrane without any pressure requirement. However, when you have a diluted draw solution here, this includes your product water as well. So the water drawn passed through this membrane is now mixed and it's not pure and clean. You have to have a very solid recovery system to recover the draw solution back to its original place, so you can have a high osmotic pressure to draw, and you need to have a product that's pure enough to be used as a drinking water. First problem we have is the membrane. We generally have flat sheet membranes that we can actually engineer by using the S parameter that as I mentioned. We can make it very thin, we can make it microvoid, and a lot of things we can use. However, spiral wound module is a big problem. We have a huge dead space. Around 70% of the surface area is lost. I will talk about it in the next one. And for the hollow fiber, we don't have a lot of companies working with it. We have two big groups, research groups from Singapore. They focus on hollow fiber membranes, but there are no membrane companies actually supporting FO membrane production in hollow fiber. The biggest problem, however, is on the separation process. As I mentioned, this separation process actually requires more energy than the desalination itself. That's why we don't have a lot of direct application of desalination when it comes to FO, but FO has been there for 12 years. So if there was a potential, we should have seen by now. So we need to find a suitable draw solution that has a very high osmotic pressure and it can be separated from the product easily, which as we saw is thermodynamically almost impossible. You have to have a magic draw solute. And the other thing is, even if you have a way to separate draw solute in a relatively efficient way, the membrane, FO membrane, is not perfect, which means you have a reverse salt flux, then you are losing your draw solute every time. Even though it's 0.01%, means after you have 100 batch, you lose 10% of your draw solute. And on the same way, you are not using 100%, you're not rejecting 100% of the salt from the FO membrane. So you are poisoning your draw solute here with salt, and you are you're leaking your draw solute through the membrane. So after 5 to 10 cycles, your draw solution is useless. You have to dump it and then put a new one. So there are a lot of issues. For the membranes, we have flat sheet membranes. A lot of research goes with the flat sheet membranes because it's easier to do and the companies are more interested. The module, you have a spiral module, plate and frame, and submerged. We tried almost all of them throughout the years and how they work. Some of them work like submerged, but then you have a problem for the packing density. You need a huge area to apply submerged process for FO membrane. And we have hollow fiber membranes. As I said, not a lot of companies are interested. Flat sheet membranes, CSM, now it's Toray Korea and Hydronautics are very interested in doing this. This is a flat sheet membrane. You can engineer the microvoids. You can adjust the S parameter, the thickness. It's very highly engineerable product. However, when you have a spiral module here, because of the shadowing effect in the forward osmosis process, these envelopes collapse on themselves, and you lose around 70% of the active area. So what happens in the laboratory, you try a little coupon, and you get huge amounts of flux, 70 LMH, 90 LMH. You roll them in a spiral wound, you get 10, if you're lucky. The reason is you don't have a good system that you can actually pack all those membranes in an applicable place. Hollow fiber membranes, they are perfect. They are self-supported, means you can keep the S parameter as small as possible. You don't need a lot of support layer. You have an excellent flow pattern because everything is flowing in one side, and you can use the surface area 100%. It's simple to fabricate, and you can have twice the packing density than you can have with the flat sheet. However, none of the big membrane companies believe the FO will actually make it in a hollow fiber way. So there's no commercial future at the moment from the membrane companies. We tried over the years many draw solutes, inorganic volatiles, organic volatiles, polymeric membranes. The idea is how we can create a huge osmotic pressure, and then we can remove this one with little low energy. So far, after 12 years, there's not one draw solute that can give us a desalination process more efficient than reverse osmosis itself. So there's a big problem. For the research, if you want to do a direct desalination, you can use FO maybe for seawater pretreatment. I'm saying maybe depending on the seawater quality. It doesn't mean that it can be applied everywhere. But you still have a lot of problems with draw solutes and draw solute recovery. And you have to look at the rejection efficiencies and reverse salt flux problems. If you want to use it as a part of desalination and reuse, so you use wastewater, treated wastewater is one side, and you dilute your seawater with this treated wastewater, which gives you a lower osmotic pressure on the seawater, so you can reduce the energy consumption in reverse osmosis. However, again, you have a problem with the pretreatments, because forward osmosis, even though people say that it doesn't foul, it does foul. It fouls sometimes more than the reverse osmosis itself because you don't use a lot of pretreatments for forward osmosis. If you use it, then you actually don't need it to use as a pretreatment for seawater. You will still need a guard membrane, probably a UF. You still need a DMF. And probably a DUF, depending on what kind of water you are using. You can just use it for reuse or reclamation, that in this case you are not trying to produce water, you are just using this one as an addition, or you can use in a niche application like they did in Australia. They used very concentrated fertilizer, so you can ship it in a small container, and on the side they can use forward osmosis to dilute it before they give it to the crops. So you can use something like that. Or you can use, like they started in China, you can use for the juice production. When you're concentrating juice, you can use forward osmosis. You can put high sugar concentration on one side as a draw solution, juice on one side, you concentrate the juice and dilute the sugar water. What do you do with this sugar water? You rehydrate dried fruit that comes from Africa or South America. So there is no waste, but there is a niche application. However, those niche applications does not include any desalination, okay, so far. Of course, we always have to look at the CAPEX, capital investment, how much you are paying. when you add a forward osmosis to a reverse osmosis process, you increase your capex around 60%. So it's a huge investment, and you have to make sure that is compensated with the operation cost savings. The second one, pressure retarded osmosis. In this case, we are not talking about water production. We are actually talking about energy production. So our end product is different. We can actually produce energy directly when we are mixing salt and fresh water. The question here, yes, this process works, but is it feasible? To know the feasibility, again, we have to look at industrial level. Even if we are doing research in the laboratories, you have to have a roadmap to see if this can work in the real world. So pressure retarded osmosis, as I explained, you are applying enough pressure not to reverse the flow, but enough to keep the site pressurized. Why we are doing this? Let's consider this as a membrane module. This is your pressure retarded osmosis membrane. You have high pressure, high salinity draw solution coming this side, and low pressure, low salinity feed solution this side. Because of the osmotic difference, you have water drawn from here, and what happens here, your pressure stays almost constant. And we proved this one in industrial scale, but you reduce your salinity by increasing flow. The basic energy in thermodynamics is PV, pressure times volume. If you keep the pressure constant, increase the volume, you increase the energy, internal energy of the system. So this is the basics of pressure retarded osmosis. And this is an osmotic to hydraulic pressure conversion. You had osmotic pressure difference here. At the end, you have higher volumetric flow rate with the same pressure. So you are increasing the pressure of this drawn water to hydraulic pressure. It's a near isobaric process, means the pressure does not change on the draw solution side, and increasing the flow rate in this direction directly increasing the workable energy. There's a good example. The first one, this is a commercial process tried by the Statkraft in Norway, and they ran this system around 2 years. They failed, and that was a very bad repetition for the pressure retarded osmosis, but I will explain why did they fail in the future. They tried mixing seawater and river water. This is their membrane process, this is pressure exchanger, this is the hydro turbine, and that's electricity. They did put 1 gigawatt capacity PRO process in place, and they ran it for 2 years. The second system came in Japan with the Megaton project. They have a full-scale process in Fukuoka Island. It's still running. In this case, instead of using seawater, they used the brine from seawater reverse osmosis, and they mixed it with treated wastewater. You can see here, if you're coming from water-scarce countries, in Norway, the seawater and river water may not mean a lot, but in most of the areas in the world, these are very valuable water sources. Those are resources, especially if you're talking about Middle East, Singapore, or any water-scarce places. So what Japanese did is they used absolute waste to run this system and to produce energy. Again, to look at it more thermodynamic based, for theoretical based, this is the Gibbs free energy that I've been talking about. If you have seawater, river water process, the maximum Gibbs free energy that you can produce or you can utilize is 0.61 kilowatt hour per cubic meter, given these concentration. However, yeah. Is it time? Okay. However, if we use a brine river water, it's 1.35. So you have a much bigger application. What they did, they used a pressure exchanger and a booster pump before the PRO and a Pelton turbine. By applying this additional process, the blue one is the regular SWRO that we all know. You have a pretreatment, you have high pressure pump, you have pressure exchanger to recover pressure from brine, you have a booster pump to compensate the pressure loss. And from here, if you apply a booster pump and a pressure exchanger, you can increase the pressure for the pressure retarded osmosis, with the brackish wastewater, you can produce energy. Here, the energy saving coming from here, but Pelton turbine has 60% efficiency, and your booster pump has 90% efficiency. Applying in a real process, you can reduce the energy consumption 14%, which is very good, and this is exactly what they did in Japan. Is it feasible? Not yet. We still have to talk about the pretreatment, and we still have to talk about the membranes, because if you have a good membrane, it means you don't have to use a lot. You can use certain amount, which increases your cost. When we look at the pretreatment, seawater brine, you don't need a lot of pretreatment. It already went through. But treated wastewater, you have a lot of organics, fulvic and humic acids. However, you can simply employ a UF membrane to treat it. And as you can see here, after months of operation, UF seems to be proven as a good pretreatment. For the membranes, flat sheet doesn't work. Even though it has a good, engineerability, it doesn't work because these macrovoids gives you a lot of flux. However, they get deformed under pressure. They collapse and they cause a huge salt leakage. Hollow fiber, now we have a company, Toyobo. They are the only hollow fiber reverse osmosis membrane productions, and they do believe that hollow fiber PRO can work. And they are supplying the membranes in Fukuoka Center. What we did in Korea, this is what I did. Instead of using two different pressure loops, we added another pressure exchanger, and we extend the loop from PRO to the inlet line. So we use the same idea we are using with SWRO, but we extend it to the pressure retarded osmosis and pre-pressurized the entire inlet. I will skip the details, but the most important one, instead of using Pelton turbine to produce electricity, we actually didn't convert it, we just exchanged it and gave all the pressure back to the system itself. In this way, we saved also from the high pressure pump, because our now inlet is not 1 bar, it's 27 bar. And if you look at the efficiencies, this has additional extra savings from the energy. And we found that this is a real process that we applied in Alicante, Spain. We can reduce the energy consumption for the whole system around 25%. So this is a very exciting one. But again, we have to be very careful. Depends on the membrane quality. Just to summarize, when you look at the low salinity seawater river water, you start with low osmotic pressure. The applied PRO pressure is low. The maximum you can get is 0.6 in optimum conditions. However, the applicable part is only 0.14. If you use seawater brine, which is a waste, and the treated wastewater, then you can get up to 1 kilowatt hour per cubic meter energy production, or recovered energy back to the system. And it comes to a new idea when you have ultra high salinity water. This is Dead Sea, but it's not limited to Dead Sea. If you know oil and gas applications, the produced water from oil and gas industries sometimes can reach to 200, 300,000 TDS. We are talking about a Gibbs free energy of mixing potential of 9 kilowatt hour per cubic meter. You can run 3 desalination plants by using this one. However, at the moment, we cannot convert this to real energy application. The reason is the optimum pressure here, osmotic pressure is around 300 bar. In order to get the maximum energy out, you need a membrane that can give you a positive flux at 150 bar, which is physically not possible at the moment. So we are looking at different applications, how to tap into this potential. And we have a new paper coming next week, hopefully from Desalination, You can check how we can try to optimize that one. Conclusions, you need high pressure osmotic difference for PRO. You need niche applications for FO if you want to use it, like juice concentration. Low turbine efficiencies limit your PRO application for energy production. And exchange is more feasible than convert when it comes to energy. And SWRO PRO process can be commercialized if you have a good membrane. Lastly, we just released our new journal. It's Case Studies in Chemical and Environmental Engineering. We have 3 papers will be accepted from this conference, so if you're interested. I'm the editor-in-chief. We are trying to combine environmental and chemical engineering, and we are trying to combine academia with industrial research in case studies. It's very hard to publish case studies. Most journals don't accept. They say it's not original, it's not research paper. However, we focus on this kind of case studies which are relevant to the real world. Okay? Thank you for your attention.